So my slides are already online, URLs on the screen there. I'm not going to reserve any time at the end of the presentation for questions. I have to describe the last year and a half of the work I've done, and I have 30 minutes to do it. This is actually the shortest talk I've ever given. So I'm going to say, please do come up and talk with me after the presentation or any time during the rest of the conference. I'd love to take questions, and I'd love to chat with you and hear about your own experiences. I just don't have time to do it in the half hour I've been given. We're already off to a little bit late start. I want to talk about how to use real computer science in the job you already have today. I'm going to start with the conclusion, which are some key ideas that are up on the screen here. After that, I'm going to work through an example of the type of work I've been doing. And finally, I'm going to talk about some other helpful ideas for finding and doing interesting work. So I like to hack on compilers. It's something I do for fun. And when I talk about this work, I get a really common response. Many people say this. They say, you know, I studied compilers or automata or data structure or functional programming in college, and you know, I just never do it anymore. And that seems like a bit of a tragedy. I mean, I use this stuff all the time. So, you know, am I doing something wrong? People say they want to do this sort of work, so I want to try and take what I do and formalize it a little bit and talk about how you find the opportunity to do fun coding in your day job, how you convince your employer or your coworkers that it's maybe a good idea to do so. Don't do this. This is a bad idea. There are some things that won't work. You can't turn it into class struggle or sneer at other people because nobody wants to hear they're doing stuff wrong. You also can't wait for people to ask you to, you know, to use formal methods because my supervisors have never done that before. I've actually never heard of it happening. Finally, if you, well, I'll give one counterexample. But finally, if you take work that other people want to do, the kind of the Rails new development, and say, hey, let's use Haskell instead, they might complain, and possibly for good reason. You probably don't need a rocket engine to power a skateboard, right? But opportunities abound. So parsing's a really fundamental technique. There are problems that don't look like compilers that kind of end up being compilers all the way down. There are some ideas for how to use computer science in your day job that I'm not going to cover because most of them involve changing your day job, and maybe that's not a great option for you. So one option for using real computer science in your day job is to go work for Microsoft Research. If that is an option for you, you probably don't need to be in this audience today. Another thing you can do is you can start your own company, and that gives you a lot of flexibility for the type of work you do. But it turns out that's really hard, and it's hard in a different way than, say, you know, compilers are. You could go be a college professor or a research assistant, but most of us really don't get handed this kind of work on a silver platter, so we have to go find opportunities elsewhere. Now, sometimes just asking the right question gets you a long way. So in 2006, I was reading this blog post on how to build data types in Haskell, and it had a statement on there that I found kind of intriguing. It said Haskell is very much not an object-oriented language. And at the time, I considered object-oriented analysis and design to be sort of an ideal to be aspired to. So I found that statement interesting. And I thought, well, you know, maybe I should go learn Haskell and figure out what's this about. And that turned out to be a really good decision. I think it kind of changed my career to just ask that question. So here's a question that you can ask your manager or your clients or your teammates. It might lead you to a good place. What are the toxic, impossible problems that hold you back and that everybody else in the company is afraid to touch? Has anybody here ever worked in a company that maybe had a few skeletons in its closet? You encountered that before? Now, you might ask, is this the kind of work you actually want to do? Well, maybe. I mean, it turns out you have almost total freedom of tooling and techniques with unpopular and really scary tasks. For sufficiently difficult tasks, formal methods might actually be the only viable solution whatsoever. It's a little bit like machine learning. You know, machine learning is not everybody's first choice. It doesn't give you precise answers sometimes, but for this broad class of problems, machine learning is maybe literally the only thing that'll give you an answer to the problem. So if you look at a problem and you want to use formal methods and there appears to be an alternative to formal methods, you need to look for harder problems. Before I go on, I want to step back here. I don't generally read my slides, but this is a kind of a lengthy quote. I want to talk about what is computer science really. And this is from the Introduction to Structure and Interpretation of Computer Programs. We believe that the essential material to be addressed by a subject at this level is not the syntax of particular programming language constructs, nor clever algorithms for computing particular functions efficiently, nor even the mathematical analysis of algorithms and the foundations of computing, but rather the techniques used to control the intellectual complexity of large software systems. So, you know, I lured you here by promising to talk about machine learning and formal methods and autonomy, and I will. But if we're going to, if we were going to talk about woodworking, we would not start with hammers and chisels. I want to step back. I want to think about the act of computing as performed by computers, like, actuaries and programmers, people like us. We compute to solve problems, and first you need to understand the problems. So I want to work through an example. I'm a consultant, and I want to talk about a problem that I solve for one of the clients I have. As a consultant, I don't necessarily have a lot of freedom for what I do. I kind of have to go in and make the customer happy and leave. So my first day on the job with this particular client, I said, what's the worst problem that you have? What's the unfixable boat anchor that's holding everybody back? I'm going to anonymize the client just slightly. I did check with them before I used their example in this presentation, but like not everybody wants their corporate logo up on next to the worst problems they have, right? So this is a large health insurance company. They sell health insurance contracts to employers, and I want to look at the process of contract renewal. You're an employer, you're buying a health insurance contract from this company, and you go to your agent and you say, well, next year we've had a few changes in our payroll and we want a few changes in the term, and the agent says, fine, and they write a new contract and they submit it to the company. At that point, it goes to a computer program that compares the two versions of the contracts, and it's got to make a decision. Should the company just write the contract and it gets passed through underwriting, or does the contract need to go to an underwriter for review, at which point the underwriter is going to either approve the contract and say write it, or they're going to say no and they're going to reject it and send it back to the agent, okay? There are lots of rules to determine whether or not the contract's going to be passed through underwriting, and there are thousands of different combinations of these rules for different products the company sells, and that's all quite reasonable. Each contract has a rate book that's based on the state and the product and the date and a few other things, and the rate book points at a set of underwriting rules that govern that pass-through. So, for example, if the number of employees has changed dramatically in a contract, it might need to go before an underwriter. And so far, so good. So how might we, as implementers of this system, store and implement these rules? The original version of the contract is stored on a mainframe, and curiously enough, this is not the problem. It kind of works okay as long as you feed the hamsters once a day. There exists a VB6 DCOM service that takes two versions of a particular contract and produces a document containing the differences between them in a custom XML format. The agents use an ASP.NET MVC site that is configured by 3.5 gigabytes of XML in 5,000 plus different files, and this is for an installed base of one site. The XML encoded rules contain something like XPath. It starts with XPath and then it adds a few other features to it that are queries over this difference document. So when the two versions of the contract are submitted, the one from the agent is compared with the one from the mainframe, the difference documents returned, and then based on the particular product, these XPaths are run over this difference document here. All told, the rate books had about 3,000 different XPath values and hundreds of distinct variations, and the customer wishes to retire all of their VB6 code, but these XPaths here are hardwired to the particular XML format that the VB6 service produces. So, 3,000 XPaths, hundreds of them distinct. strewn across thousands of products. I mean, it sounds kind of awful, but actually it's a fairly successful business. They've been in business for decades. They're making money. Software isn't their product, and stuff accumulates, right? So lines of code is not a great metric, but it does measure maintenance impact pretty well. The existing behavior of the system has to be assumed to be correct because there's no other comprehensive specification for what it does. Also, this has to work the first time or there's no hope. I'm talking about changing tens of thousands of lines over thousands of products, hundreds of distinct rules. You can't QA this if I'm introducing behavior differences and lots of bugs in each variant of this. I'm aiming for bug compatibility with the production system because it's the only comprehensive specification in existence. If an end user notices the changes I've made, or even to some degree if a QA does, I've kind of failed in this project. So the first step here is domain model recovery from the 5,000 plus legacy XML files. I have all these files. Well, what's in them? Is it even well-formed XML? Well, not always. The business analysis has only been captured in code. Now, this paper on the screen, which I have hyperlinked on the bottom, and if you download the slideshow, you can get the hyperlink, attempts to explore the question of to what degree can a business domain be recovered from source code alone when there's no other comprehensive documentation. They took a very well-understood domain, which is project management, and they looked at some open source products, and they said, how much of this domain can we recover from the source code alone? Turns out you can do it pretty well. Some people really hate legacy code. They don't like to see it. They don't like to work with it. I see it as a really fertile ground for data mining. I like to say there's gold in that brownfield. There's real domain knowledge in there. It's been captured in a not-so-great format, but it's oftentimes the only place that you can find decisions that BAs made 10 years ago. The source format is kind of, not so great, but this works in production most of the time. It's not well structured, it's not, like I said, it's not always even well formed, but it's kind of been beaten into submission with 10 years of bug fixes as the company evolved. So how do you recover dozens of domain models from thousands of files? My process for attempting something on that scale is you start with sweeping overgeneralizations, and then you write really lightweight tests to show where your overgeneralizations are wrong. So step one, I wrote down what I thought was in the file in F#, and F# forces me to be very precise about what I think, in this case, there's a string that might be present, and then there's other cases there's a string that must be present. I used enum types for things that must have a specific value. And then I wrote a deserializer. And the deserializer just tears through all of the XML files. And if I can deserialize from the data in every single one of those XML files, then I have proven my domain model correct by construction. And now, of course, this does not work the first time. As I run this, I find cases where there are angle brackets missing in the XML file or where my domain model is wrong. And so for each specific case, I need to look and say, is my domain model that I created here incorrect, or is the actual XML file wrong, in which case I got to go fix that. And in many cases, I have to look into the C# code in the production system and say, is this thing deserialized in a case-sensitive or case-insensitive way, because it varies upon the particular area of code that we've touched here. There is one other wrinkle I'll throw out here. The company has an application architecture team, and they are totally opposed to new F# development. They want everything in C# and JavaScript. This turned out to be totally inconsequential for the project I'm doing, because as long as I'm checking in C# production code, they don't care how I wrote it. If I can produce C# production code that's defect-free with F# in a problem that nobody thought was solvable to begin with, that's great, and they're fine with that. I have on the slides from time to time some code, and I know that's probably impossible to read from the back, but here's the thing. This is not an open source project. It's work I did for hire for a real customer. I can't just throw this stuff out on GitHub. At the same time, I didn't want to leave you with nothing, so if you're interested in seeing some of the code I wrote, I've put some on the slide. You can download it and look at it in a little more detail when you can see it closer up. The deserializer here is just a handwritten parser that that I wrote. As a lexer, I use the .NET XML reader. It's super fast because it doesn't actually use a DOM. It just emits a stream of XML tokens. The grammar is defined by the F# types I showed earlier and the structure of the XML files. And we instantiate this with lightweight code generation in .NET. Why use a handwritten parser? Well, because there's so many different ways that the production C# code deserializes this XML. At any given point in the code, it might be case sensitive, case insensitive. It might be deserializing the types from attributes or from nodes in the XML. I'm aiming for bug compatibility with the existing C# deserializers, of which there are many. I use heavy use of memoization and parallelization to make reflection cheaper. I noticed that because of the reflection, the process ended up being CPU bound, and because I write idiomatic F#, I was able to change about 6 lines of code in the entire program to make the process run in parallel, and then I could use 100% of the cores in the machine. It takes about 30 seconds to deserialize roughly 150 megabytes of XML in a machine with a mechanical hard drive. So let's look at one specific case of underwriting pass-through rules. There's one example here on the screen which says, you know, if your address changes, we need to possibly forward this to an underwriter. So you can see there's some embedded XPaths in the XML here. And then just which files this thing appears in governs which types of contracts the rule is going to apply to. I need to rewrite this entire thing as equivalent C#, and then I need to go and remove the XML anywhere it appears in the files. So my process here for doing large repetitive tasks efficiently by machine, you start by doing it by hand a few times. You remember Victor Klang's conjecture from yesterday. You have to be able to do something in order to be able to do it by computer. Or by programming, and then you learn about the variance of the problems and the parameters to it, and you try and generalize. For a specific case of the generalized problem, what are the unknowns? You might even need to write a program to figure out what the unknowns are on a particular case. And then there will be things that are tedious to do by hand, and you automate. And then you repeat this entire cycle over and over again, becoming more general, more efficient, and much, much faster every time you do this. I have hundreds of combinations of these rules to get through. So first you do it by hand, and then you automate. I rewrote a couple of rules by hand. It took about a week each, and I learned a lot in the process. I need to produce C# code that looks something like this. There are 2 parts here. One is called onApplies, and this projector is a little too high, so you can't quite see. Well, let's get that to where you can see the entire screen. So one part of this is called onApplies, and the other part is called onValidate. The onApplies says, should a particular rule apply to a particular contract at all? And onValidate says, given a particular contract, should that be forwarded on to an underwriter, or should it go through to the next rule? Creating code like this isn't hard, but I have to do this hundreds of times, and I cannot make a single mistake in the process. One of the things that I learned when doing the rules by hand is that determining when the rule applies is really, really hard to do by hand. So if I look at these XML files and I find a particular XPath in the XML, there will be other XPaths that are kind of like it. They might vary by white space, or they might vary, you know, by parameters in the XPath. And I need to produce a comprehensive list of products that a particular XPath appears in. And then I need to come up with a specification that takes that list and represents it as a predicate over a product. So a rate book references multiple underwriting rules files. So I take my XPath that I'm interested in. I figure out which underwriting rules files it appears to. I fix up the references to the ratebook files, and then I produce a list of ratebooks that have the rule and a list of ratebooks that don't have the rule. And then I need to infer a specification from that for when the rule applies at all. Some specifications are really simple. It might just be for a particular state or a particular contract type. Others are quite complicated. This rule applies in this state, on this contract type, on or after this date for a certain form, and other things for other states. How can you do that generally? I ended up using a decision tree. This is a sample decision tree for your probability of surviving the Titanic. But basically, the idea here is that at each step, we look at the rate books that have the rule, and we look at the rate books that don't have the rule, and we say, are there things that stand out as allowing us to sort these well? So what we want to do is, for example, we might look at the state, and we might say, if I divide these rate books up by state, do the rate books that have the rule and the rate books that don't have the rule get more organized? Have I decreased the entropy or increased the information gain here? I choose the best feature, whether it's state or the product type or the date. And if that perfectly divides the rate books that have the rule and perfectly divides the ones that don't, then I'm done. But if it doesn't, then I go on to the next feature. And I produce a tree specification that lets me understand when a rate book has the rule and when it doesn't. So here's a sample specification tree that says, you know, this particular rule applies to Michigan HMOs and Ohio HMOs and Texas HMOs and Utah HMOs. And you might look at that and you might say, well, that looks better than just a list of rate books, but can we make it simpler? So the next phase of this project is optimization. We want to take something like this on the top and produce a logically equivalent statement on the bottom. And this thing down here probably captures the original statement from the business analyst some 10 years ago much, much better than the list of rate books that I started with. This idea is really important here. Probably half the F# code I wrote is just dedicated to making sure that the sweeping assumptions that I've made about the business analysis, the business motivation, and the correctness of the analysis code that I write are actually true. The other half of the F# code is producing the shipping and the test C#. So I do something I call proving the specification, which says I start with that original list of rate books that have the rule and rate books that don't have the rule. Then I take my specification and I run it on all the rate books, and I ensure that the lists that I get out of those which have the rule and those that don't are actually the same. My machine learning code, my analysis, my optimization is not perfect. I'm human, I make mistakes, but the proof system is really trivial. This is the entire thing here. It's exhaustive, and it always catches bugs in the former. So onto the rule itself. The so-called XPath, as I said earlier, is not standard. They've added some additional features and templates in it that existing XPath parsers don't handle. So So I ended up writing my own lexer and parser. This turns out to be really easy because I don't have to parse every XPath in the world. I have a few thousand files, and that's all I have to handle. So it's much easier than the general case of XPath parsing. And I take what's in the XPath and I turn it into an abstract syntax tree. From there, creating code like this, like I said, isn't hard, but we have to do it hundreds of times and perfectly. So I take that abstract syntax tree and I pretty print it as C#, and then I take the original list of rate books that had the rule and I generate in unit tests that run against the C# code. So here's the result of having done this for a year and a half. We've had no defects go to production ever, and we've never had a code-generated bug, which isn't to say it's entirely perfect. The onValidate function has to call existing C# services in the production code. Some of those services didn't exist, and I wrote them by hand, and I do make mistakes, but I have the world's greatest QA person, and he's managed to catch all of my mistakes that I didn't catch myself before they went to production. One other mistake I made from time to time that was a little bit annoying is that I wrote up work items for each rule I changed to give to the QA, and sometimes I wrote those incorrectly. And after I made that mistake a couple of times, I started generating the TFS work items for the QAs as well. So at this point, I'm generating the C# production code, the C# tests, and the TFS work items. I started thinking if I could only teach the thing to snark on Twitter, I would be totally obsolete. So in summary, this is exactly the kind of code I enjoy writing. I wrote domain model recovery. I was able to use a lot of F#. I wrote 2 parsers in Elixir, an optimizer for abstract syntax trees. I did some machine learning and a code generator. This is fun for me. I enjoy this stuff. But more importantly, my customer enjoyed it as well. They had sort of accepted all these gigabytes of XML is something that they were never ever going to be able to get away from until they threw the entire system out. And I've been able to show them some light at the end of the tunnel. I also ended up with the only model of what is actually in those XML files, that shows how the system behaves in fact in production instead of how it's intended to behave. And interestingly enough, having this model in F# means that other developers are able to write arbitrary queries over the data model. So when they had ended up with a piece of C# code that sort of disappeared into the XML before, where they weren't able to to do find references and just figure out what's in there. Now they can write queries over that XML, and it helped other developers remove the XML dependency from the code that they were working on. And it gave the company the foundation for how they might remove the XML altogether in the future. So they ended up being very happy with the work. Stepping outside of that particular narrative, I want to talk about a few other tips that I found that are helpful. Obviously, using computer science in your day job, step 0 is to learn computer science, but it's a big field, and we're always asking, what's the next interesting thing to learn? So one way to sort of guide that exploration is look at your employer's business strategy. Ask yourself to what degree software contributes to that business strategy, and look for gaps between technical implementation and execution of business strategy. You want to sort of maintain a mental map between your day job problems and the formal methods. Look especially for technical problems that are considered too hard, too big, or too fragile to solve. When faced with old and brittle code that people are afraid to change, period, one thing that I found really interesting is computers are super fast, right? You can often push every possible value through legacy code and just look at what comes out. And then you can do machine learning or statistical analysis over the result, and you can often sort of derive the specification for what that brittle code was doing, which gives you a much better way to replace it than just sort of tinkering and hoping you don't break much. That's in fact how I did some of the changes with the XML here. Also, one thing really important to consider in mind is that when you're looking at introducing a new technology in a company, and maybe the company is a little nervous about that, they often have much stricter restrictions on what you can put into production than on the type of code you write that is not production code, but that learns about production code. So a simple example that everybody understands is unit tests. If you are wanting to introduce F#, you can, for example, use Canopy to run your browser tests instead of raw Selenium. And people are often much more open to that than using F# in production right off. But beyond unit tests, you can write compilers, you can write static analyzers, you can write proofs, and you often have considerably much more freedom in your choice of tools for that type of code versus production code. Another thing that I found just increases my enjoyment in my job quite a lot is we try and start a clique. We have lunch and learns on topics that are interesting to us. A bunch of us took the Coursera machine learning course, and we ended up having a study group for that at work. This has been super fun for me. I work at my current client's an insurance company. The insurance company has actuaries. They have research people who actually know a whole lot more about math than I do, and they're a ton of fun to talk with. And we've been able to sort of put our heads together and identify opportunities for machine learning at the insurance company in the future. So stepping outside of the developer circle and looking for other people who are just into math has been really productive for me. As formalists, though, we tend to look for provably correct solutions, right? And we may look askance at less rigorous efforts that other people use, but correct solutions may not be the best choice if they're expressed in a language that only you speak. Correct solutions may not be the best choice if nobody wants to listen to you, period, because they think you're a condescending jerk. The best solutions are those which really solve the team's problems. It's worthwhile to just stop and say, where is your pain? Regardless of method, where's the opportunity to make your colleagues' lives better? You want to deliver something useful no matter how you got there. As a consultant, I could be gone tomorrow, right? I have to leave something valuable behind. Which isn't to say don't use powerful stuff. Some of the code I wrote was quite abstract, but I made the decision to try and keep this code in the code generator, which is going to be thrown away at the end of the project, and not the generated code. The generated code and tests I make need to be maintainable and understandable by everybody in the company. If you're the sort of person who needs case studies to show your manager to say, you know, that this stuff really is valuable, I have a couple of references up here. At the risk of repeating myself, look for unpopular problems, look for impossible problems, look for code that's too big or too brittle to maintain. And when it's hard to solve a problem with code, use code to write more code and code to make sure that that code's correct, and everything works out in the end, I found. Look for power tools. This is a little information about how to talk with me, and I am 1 minute over my time. So thanks very much for coming out. I hope I have the opportunity to talk with more of you during the rest of the conference. And if you have any questions, please run up and chat at lunch. Thanks a lot.